Good morning, students.
Good morning, ma'am.
Good morning, Jason. 53 are present. We'll wait a few more seconds for others to join. Krishna has left. Okay, students, let's start. Uh, Appreciate all of you. You're already there present, but I expect that you're present both physically and mentally. Okay, fine. So we will move on with our class. This is lecture number 8, and we are proceeding to our next topic of discussion, that is rectifiers. So by the end of this class, you will be able to define rectification and describe the working of a rectifier circuit. Okay, simple rectifier circuit. And I believe that you are already have some basic information about rectifier circuit, what you have studied in PU. So we will proceed with that information and background knowledge. We'll proceed with the discussion. And again, just to remind you again, as I have kept my slides open here, I'll not be able to track the chat there. So if you want to stop me, if you want to talk to me, please unmute yourself and speak. So that is the common announcement what I have to do every class. So I hope you are attentive, and I expect you to be attentive. So which is because this is a very important topic, and to understand basic electronics, you have to understand basics first. Okay. So first, let us have a small recap of the previous class discussion. So we discussed about voltage regulation there in the previous classes using Zener diode. So we observed the two types of regulation, line regulation and load regulation. Line regulation, we defined it to be the typical ratio of the change in the output to the corresponding change in the input, right? So in line regulation, we know there will be variable input voltage, and the output, at the output the load will be fixed, right? So to calculate the percentage of regulation, that is in line regulation, generally we will take change in the output with respect to change in input into 100 will be the percentage value. So in load regulation generally specifies how much is the variation in the output voltage for variation in the load current, isn't it? So if the load current is varying between, say, minimum value to maximum value, where minimum load current indicates no load at all, and the maximum load current indicates when there is full load or maximum load. So in using that reference, the load percentage load regulation will be calculated using this equation there, VNL minus VFL by VFL into 100. So that is a small recap of the previous class discussion. So we'll proceed with the rectifier circuit. So coming to the most popular application of diode, that is rectification. So what do we mean by rectification? We are already familiar, I think. It is simply, just to simply define it, rectification is a process of converting alternating current to direct current, right? So this simple definition we are already familiar. I believe all are familiar with this. So what exactly happens here in rectification is it involves a device that allows current to flow, say, only in one direction. Okay, so using such device, where we are familiar that the semiconductor diode what we have come across till now, it's a device which will allow the current to flow through only in one direction, right? So that becomes the popular application of diode, that it is used mostly in rectifier circuits. Okay, so the rectifier circuits, broadly they are classified into two categories: half wave rectifier and full wave rectifier. So half wave rectifier is the one where the conversion takes place only in the, say, half of the cycle of the input, and in a full wave rectifier, in both the cycles, that is positive half and negative half of the input signal, the rectification takes place there. That's why the name half wave and full wave, so which we will discuss in detail in the coming classes. So rectifier are fundamental to most of the circuits here, because we know the different devices, electronic devices what we use, they all depend on, say, some low value of power supply, right, or low voltage of DC voltage. So we are familiar that uh, the AC grid what we use in most of our households, or say even the industries or wherever, the AC grid is of, typically the line voltage in India is 230 volts with 50 hertz, right? So the electronic devices what we are talking about, it can be, say computers, or say some electronic device, or any equipment. Name any electronic device, you know, they operate on low DC voltage, right? So for that there has to be some conversion. Say you need a circuit where you have to convert this AC power to a DC level, where the rectifiers come into picture. Okay, so there where there is conversion, or if you have to say bring to a lower level, okay, change in the voltage, okay, there the rectifiers come into picture. Okay, or converting AC back to DC, or say DC back to AC, wherever such conversions are there, you come across rectifier circuits there. So, in order to understand the vast applications what we are coming across now, the conversion of the power from one level to another, or one type to another, every circuit includes rectifier. So we need to know what is rectifier and how it happens. Okay, so that is about brief of what is rectification and its use there. So observe this block diagram here. I hope you are able to relate things. This is the block diagram of a simple DC power supply. Say there are components called transformer, rectifier, filter, regulator, and the load. Right? So what is the work of the DC power supply there? It brings down the voltage level from, say, 230 volts 50 hertz to the required level of the voltage at the load. So here the figure is taken from the textbook. So here the voltage mentioned here, the AC supply mentioned here is 120 volts 60 hertz. So which is of other major countries. All right. So for India, it is 230 volts, 50 hertz. So observe here what happens. So in the DC power supply, right, the outlets what we have is 230 volts, 50 hertz. All right. So that has to be brought down to constant DC voltage, right? So there are different stages that happens here. So just to give you a glimpse of that, all right. So the voltage used by the different electronic circuit, what I just now mentioned, it can be say computers, it can be industrial controllers, or it can be any instruments or equipment, all work on different DC voltages, different level of DC voltages, right? So generally that 230 volts has to be brought down or stepped down, which happens from the transformer. So transformer generally steps down the voltage. Again, it depends on the application, whether if the signal has to be stepped up, then accordingly the transformer can be uh, used to step up the voltage as well. So for that, we have the basic information that a transformer changes AC voltages based on the number of turn ratio in between the primary and the secondary, right? So, and we are also familiar that, say, if the secondary has more number of turns compared to primary, then the output voltage across the secondary will be higher and the current will be smaller, isn't it? Yeah. And if the secondary has few turns compared to primary, then the output voltage across secondary will be lower and the current will be higher. Are you with me so far? Are you agreeing with me? Are you agreeing with me about the transformer and its conversion? So
Yes, ma'am.
yeah,
Yes, ma'am.
yeah. The next stage here is, as you can observe from the power supply block diagram there, it is the rectifier circuit. So rectifier, we know it can be a half wave rectifier or full wave rectifier. So in the figure, it is shown half wave rectifier there. So this rectifier circuit converts this AC input voltage from the secondary of the transformer to pulsating DC. Okay, so pulsating DC because there is variation in the output signal, but only in one direction. That is during only, say it can be only positive cycle for the half wave rectifier, or it can be for both the cycles in full wave rectifier. Okay, so the example shown here is for half wave rectifier output voltage. Now the next component what you can observe here in the power supply is the filter circuit or the filter block, so which will eliminate this fluctuation from the rectifier output. Okay, so this smooths out the output DC voltage that we have got from the rectifier circuit. So filter smooths the output of the rectifier, where it will say bring the ripple content or reduce the ripple content in the output voltage. Okay, so again that we will discuss in detail in the coming classes. Next is the regulator circuit. Now you are already familiar. Regulator circuit is the one, even when there is variation in the input voltage, the output across the regulator will be constant, maintained constant. So regulator circuit is used to maintain constant DC output voltage. Now again, based on the load and its requirement and the requirement of the level of the DC voltage that is expected from the uh, load. Load here means you can imagine all the devices that are connected. It can be computer, it can be mobile charger, or it can be any equipment, any electronic equipment. So based on its requirement and level of the voltage required, so this power supply, the whole block diagram works to reduce this 230 volts input voltage to the level that is required by the electronic circuit what we use. Okay, so all these conversions, all these stages take place in the power supply what we use. So, um, so as you know the importance now, as you understand the importance, that bringing down the level of the voltage or the current from say one level to another, there should be rectifier in that. Okay, there will be rectifier, there will be filter and a regulator to bring down to a, a different level. So because of the ability to conduct current in one direction, okay, and block the current in the other direction, diodes are used in the rectifier circuits. So as you can observe, this is a simple half wave rectifier circuit. All right. Now observe here, there is a diode connected to AC source and there is a load connected. Okay. So this forms the half wave rectifier circuit. Please observe, please pay attention. This is very important topic and basic. If you understand this, you will understand all further classes. Otherwise, it will be very difficult. So those who have difficulty in understanding electronics, please pay attention. Okay. So there is a diode, there is AC source. Note here, there is AC source and there is a load RL. And please note here, the ground level will be common there. Okay. The wherever you have ground, it means it is a single same point electrically. Okay, single ground point there. So AC source connected to diode with the RL load will be your half wave rectifier circuit. Now observe what happens. Typically, if the diode used is a ideal diode, now you should be in a position now to understand what's the difference between ideal diode and the practical diode. Okay. Now, assuming if the diode used in this circuit is a ideal diode, so when the sinusoidal input voltage goes positive, okay, we know sinusoidal signal means the signal will be varying continuously with respect to time, right? That's why we call it as sinusoidal signal. So whenever the sinusoidal input V in, take it as V in, when it goes positive, now the diode will be forward biased, isn't it? So when the diode is forward biased, we know it allows the current to pass through, okay, and it acts as a short circuit there, right? So the whole current is allowed to pass through the diode. So it acts as a short circuit. Now observe here, there is RL connected, the load is connected. So the current produce an output voltage across the RL, right? The current flowing in the circuit will produce the output voltage across the RL. Across the RL means where you measure the output voltage with respect to ground here. Okay. Now observe here, the output is shown here, which has the same shape as the positive half cycle of the input voltage, right? So during the positive half cycle, whenever the input of the AC signal is positive, whenever it is positive, the diode is forward biased. When it is conducting, current flows through the circuit, and due to the current flowing through the circuit, the output appears. The output here is V out. What you can observe here on the right hand side is nothing but which looks similar to the positive half cycle of the input voltage. See, it is as good as, say, when we say diode is conducting, it is a short circuit, right? So what you measure at the output will be nothing but the input. So you have to understand in that way. Because of the short circuit there, the output follows the input. So the whole the positive cycle will appear at the output. That is the point there. Whereas in the negative cycle, observe here, when the input goes negative, during the second half of its cycle, diode will be reverse biased, right? Diode will be reverse biased and there is no current flowing through the circuit. So the voltage across the load will be 0. When there is no current, the voltage across the load will be 0 because The circuit will be open here, right? So there is no current flowing through, no output voltage, so you won't get any output at across the output terminals for the negative cycle. Okay, so the net result what you can observe here is, so in the rectifier circuit, only during positive half cycle the AC input voltage appears across the load, right? So since the output does not change the polarity, the output will be, say, pulsating DC with the same frequency as the input. So what you get at the output will be something like this. So the for 50 hertz signal, the output of the half wave rectifier is shown for 3 input cycles. Okay, so only at the positive cycle of the input, the output appears. In the negative cycle, output doesn't appear, and the output is shown for 3 cycles there. I hope you are able to relate things, right? So coming to average value of the output voltage. So typically, the average value will be the output, the average value of the output will be measured from the DC voltmeter. Okay, so mathematically saying, it is determined by um, by finding the area under the curve over one full cycle. Okay, so it is actually given by V average is equal to Vp by pi. So this we will derive shortly how we arrive to this point. But at this point, I want you to understand the average output voltage is nothing but which we generally measure from the DC voltmeter. Okay, so which is given by Vp by pi. Okay, understand that. We will derive the expression for this. How do we get this Vp by pi? We'll shortly derive the derivation there. Okay. Now, whole question. Quickly answer this question. What is the average value of the half wave rectified voltage in the figure shown? Quickly, I'll be expecting answers in the chat box. Very good. Yeah. Ashwija, give me the value. What is a value is the question. Very good. So all are attentive, paying attention. Okay. Yeah, this class is very attentive. Good. Yeah. Let me see how many responses here. Oh, I think the whole class, very good. Yeah. And I hope you're following things. I'm happy you're attentive. Okay, let's move on. Now, what is the effect of the barrier potential on the half wave rectifier output? Okay, now observe that when we started the discussion, we said the diode used in the circuit, assuming it to be idle. Okay, so if at all, if a practical diode is used in the circuit, then we have to consider the barrier potential of the diode as well, right? So assuming the diode is a silicon type of diode, and we know the barrier potential of silicon diode is 0.7 volts. So then in the half wave rectifier circuit, the output will be again varying with respect to the barrier potential. That means there is an effect of the barrier potential on the output of the rectifier circuit. So this is what happens. What will happen? During the positive half cycle, the input voltage must overcome this barrier potential, right? Okay, before the diode becomes forward biased. So the result is that the half wave output will be 0.7 volts less than the peak value of the input. So the expression is given there. All right, I'll repeat. During the positive half cycle, all right, the input must overcome this barrier potential to make the diode to be in forward biased. So resulting in 0.7 volts less value in the peak value of the input. That is, output will be 0.7 volts less compared to the peak value of the input. That is what I mean to say. So why is that so? Can anyone answer? Why is it so? Why will be the...
Ma'am, the voltages get distributed in a series circuit.
Not very precise, Ashwija. Not very precise. Can anyone else try? Why will be the...
Because the diode requires 0.7 volt to conduct.
Correct.
So it absorbs 0.7 volts. So
Absorbs.
remaining like it takes that 0.7 volt and remaining voltage is supplied to RL.
Okay, yes, you are 90% correct, but the word what you used, absorbs, is wrong. Okay?
It will resist, ma'am.
It will resist, Avin. What do you mean by it? Resist means what? Yes, Avin.
It will act as a resistance for the remaining 0.7 volts. It won't conduct 0.7 volts.
Won't conduct, correct. It won't conduct. Okay. So, yeah. So we are familiar, say, the diode, its barrier potential is 0.7. So till the input signal reaches 0.7 volts, okay, the diode is still not forward biased, right? That is, it is not conducting. Again, that means there is no current flowing through it. Okay, so till the input voltage reaches 0.7, the diode is still not conducting. So when the diode is conducting, when the input voltage crosses this 0.7 volts, right? So when the diode is conducting after that point, then it is nothing but a short circuit in the circuit, right? So at the output, whatever is applied is appearing at the output. So the blue line is your input signal, all right, and the red is the output, what you can see there. So observe here, this small red line, which is horizontal line, this is the value till where diode has not started conducting till 0.7. So all the term that what you use there, it is resisting or it is absorbing, no, that is the wrong words there. Okay, till 0.7, the diode is not forward biased and it is not conducting. Once the input voltage reaches 0.7, that is when diode is forward biased and it starts conducting. Starts conducting means it allows full current to flow through, or in other words, it acts as a short circuit. Okay, so when the, I'll go back this one. Okay, when it is short circuit here, so the whole input signal, what is applied there, it is appearing now at the output, right? So this red line is your following input values, that is after 0.7, all right? And obviously, since this is a half wave rectifier output, so the output will be only for the positive half cycle. In the negative half cycle, as you can observe, there is no output there. Again, in the next positive half cycle, the output appears. Okay. Now, when we observe the peak value there, this blue color peak is your input signal, right? The secondary, instantaneous secondary output voltage there, VP in. And red is your output from the rectifier circuit. So VP out, the red one, will be equal to VP in minus 0.7, right? So that is what I mentioned. The peak of the output from the rectifier will be 0.7 volts less than the input. Okay. So that is what is explained there. And I hope it is clear. Why is it so? Because till 0.7, the diode will not be conducting. Only after the input reaches 0.7, the diode starts conducting. So there will be this difference in the peak values. Okay. All right. I hope it is clear from the figure there. Now, next poll question. Answer this. Find the output voltages of each rectifier or the indicated input voltages as shown in the figures. And I'm expecting answers there. Find the peak output voltage for the rectifier for the indicated input voltages. What is VP out for both the cases is the question. Okay, I'm not getting any answers.
Ma'am,
Should I repeat? Oh, is it not visible? Yeah.
Ma'am, the screen was not visible.
Okay, now is it visible?
yes, ma'am.
Okay. Find the output voltages of each rectifier for the indicated input voltages. Oh, still there are no answers. Why so? Oh, that means you were not attentive. You didn't see the previous slide. What will be VP out? None of you, is it? Okay. Bhumika, Meville, Ketan, correct? Okay, that is you can give both the answers together. Both the answers together. Both the answers of both the circuits together. Correct. Okay. So when I pause, I think you will come running back to the system, huh? Wherever you were. Is it? Okay. Yeah. I think I've got the answers. Yes. Yeah, stop now. Let me take this. Let me see how many of you were attentive. I'll stop here at Suhag. Okay. So others who didn't reply, you were not there. Okay, fine. Okay, let's move on. Oh, yeah, you have observed that the answer is 4.3 and 99.3, right? So what do you understand? Should we neglect this barrier potential 0.7, which is very small number, right? So if you observe from both the examples there, 100 minus 0.7, right? So the output voltage was 99.3, and 5 minus 0.7, the output was 4.3, right? So neglecting this barrier potential would be, will cause much of the, say there will be significant error in the calculation of the circuit, right? The parameters in the circuit. So for especially in the first case, so the difference is too much there, right? So that would be, if you neglect 0.7 there in the first case, there will be, say in the calculation of further parameters, there will be significant difference or the error compared to the second one, all right? So yeah, generally we do consider the barrier potential of the diode used in the circuit for different calculations. And the final parameter, what we have to discuss here in the rectifier is this peak inverse voltage. Peak inverse voltage is nothing but the maximum reverse voltage that the device is able to withstand, okay, during the reverse cycles or reverse voltages. So as indicated in the figure here, in the every negative cycle, which is repetitive, right? So there is peak reverse voltage, right? And we know during the reverse voltage, the diode will be reverse bias. So this maximum reverse voltage should be, the diode should be able to withstand it. So otherwise we know there is a chance of breakdown happening, right? So the device, the diode that we use in the rectifier circuit should be more than the rating of the PIV of the circuit, that is peak inverse voltage of the circuit. So we have to check the PIV of the circuit, that is input voltage, and based on that we have to select the diode whose ratings will be, say, around 20% higher than the PIV value here, okay, so that it would not damage the device during the negative cycles. So that is PIV, peak inverse voltage. Peak inverse voltage is nothing but the peak value of the input voltage the diode must be capable of withstanding during the reverse voltages. Okay, so all these are important parameters what we have to remember during the rectifier circuit. Let me change my presentation. Can you see this circuit there? Is it visible?
Yes, ma'am.
Can you see this?
Yes,
Yes,
ma'am.
ma'am.
Okay. Yeah. So typically, So observe this half-wave rectifier. So this again I'm taking directly from the textbook. So you can expect such diagrams in the future there. So the circuit shown here is the half-wave rectifier, where the input is, there is a transformer connected to at the input, okay, where you have the instantaneous supply voltage, the AC, okay, V1, and V2 is your instantaneous secondary voltage there. So the positive terminal of the secondary of the transformer is connected to the diode, and there is a RL connected, that is the load, all right, and the output what you measure is V out there, all right. So typically this will be your response or the output waveform what you expect from the half-wave rectifier. So this is your input, which is nothing but, you can say this is your instantaneous secondary voltage, okay, the voltage across the secondary of the transformer here, which we say this is the input to the half-wave rectifier circuit. So this is your input signal, sinusoidal input signal, and the output what you can see here, this is your current, okay, what you get during only the positive half cycle, and this is your voltage what you get during only positive half cycle, okay. Obviously the amplitude of the current will be less compared to the voltage, right? So let's go on with the derivation and the working of the circuit there. So assuming V1 to be instantaneous supply voltage. Now I'm talking about the derivation part of the topic. Please pay attention. Assuming V1 to be instantaneous supply voltage, all right, and based on the transformer information, we know that the voltages at primary and secondary, that is the ratio V1 by V2 will be equal to N1 by N2, right? N1 by N2, where N1 is the number of turns in the primary and N2 is the number of turns in the secondary. I'll repeat, V1 by V2 will be equal to N1 by N2. So from that, we get V2 will be equal to N2 by N1 into V1, isn't it? Right? So taking V1 to be our instantaneous supply voltage, let us assume to be Vm sine omega t, where Vm is the maximum or the maximum amplitude of the voltage, all right, and sine omega t because it is a sinusoidal signal, all right. So taking this relation, V2 is equal to N2 by N1 into Vm sine omega t, substituting V1 there, all right. So during the positive cycle, when C becomes positive here, diode will be forward biased and the current will flow in the path from C, D1, E, F, D and back to C, correct? So that will be the path of the current. I'll repeat, when this point C is positive, okay, during this positive cycle, the current path will be from C, D1, E, F, D and back to C. So that will be the flow of the current and the direction of the current flow. So during negative half cycle, when this C point becomes negative, when C is negative, then diode will be reverse bias and it will not conduct. So there will be no current flowing through and the output will be zero, isn't it? So during the positive half cycle, when there is current flowing, so how do we get the relation? What will be the current? So apply KVL there. Applying KVL. Okay, let us take the equivalent circuit. Please note down. We are now deriving the expression for average DC output voltage and output current. We are deriving expression for average DC output voltage and output current. So we are starting from our discussion, taking the equivalent circuits when the diode is conducting and diode is not conducting. So here observe that the diode is replaced with this internal resistance RF. Diode in the circuit is replaced with internal resistance RF. All right. So when I apply KVL in this loop, okay, my KVL will be minus V2 plus I naught into RF plus I naught into RL will be equal to 0. Am I right? Are you with me?
Yes, ma'am.
Yeah. So from that, taking I naught outside from that relation, please write down there I naught relation, I naught taking outside, inside the bracket you will have RF plus RL. Okay. And on the right hand side, you take V2. V2 will come right hand side. So my I naught will be equal to V2 by RF plus RL. Are you with me? I naught will be equal to V2 by RF plus RL. Okay, that is my output current I naught when diode is conducting. Okay, and observe the second circuit there, when diode is not conducting, I naught will be equal to 0. And I'm expecting that you're noting down all these points. We are deriving things now. Okay. Now, from the relation, what we have now, V2 is equal to N2 by N1 into Vm sine omega t. Okay. Taking this ratio N2 by N1 to be equal to 1, taking ratio N2 by N1 to be 1, then we have V2 is equal to, small v2 is equal to Vm sine omega t. Okay. Now from both the conditions and from the output there, from the waveforms what we have, the output current I naught, it will be equal to Im sine omega t during the relation 0 and pi. I'll go back to the waveforms there. Okay. This is your response. So I naught, the output I naught will be equal to Im sin omega t between time period 0 to pi, and it will be 0, the output current will be 0 between the time instant pi to 2 pi. Correct? Okay. So coming back here, coming back to the relation. So we have current in the two time instants there between 0 to pi and pi to 2 pi. So 0 to pi, it will be Im sin omega t, and 0 between pi and 2 pi, where Im will be the current, what you are replacing here in the equation, Vm by Rf plus RL. Okay. So Im is your peak load current or the output current. To find the average DC to pi. Okay. Yes, somebody speaking. Let me. Anyone wants to say something? I didn't observe what was that. Okay. Okay. So area under one cycle of I naught by period of I naught. So you will integrate between 0 to 2 pi and substitute the current there, I naught d omega t by 2 pi. The total period is 2 pi. Okay. Now we have the current in two time instant, that is between 0 to pi and pi to 2 pi. So split that and substitute that current value there. All right. Please note down. So 1 by 2 pi taking outside. So within the time period 0 to pi, that is integration between 0 to pi, your current is Im sin omega t d omega t, and plus between pi to 2 pi, that is integration between pi to 2 pi, the output is 0. Okay. Now integrating the first term there, taking Im outside, which is constant, Im by 2 pi will be outside. So integrating 0 to pi, so integration of sine is minus cos. I hope you are able to substitute what is cos pi and cos 0. Is anyone speaking, or I'm getting a ping there, but I'm not able to understand what is it. Is anyone trying to speak? Okay. So that is your average DC output current, IDC, Im by pi, where Im is your peak value of the current divided by pi. So this we had discussed earlier during the initial class. Now observe here, average DC output voltage, substitute VDC. IDC is your DC output current. VDC will be simple Ohm's law there. V is equal to IR. So VDC will be IDC into RL, right? So IDC substitute there, Im by pi. So just simplifying things, where Im you are replacing with Vm by Rf plus RL. Okay. So the average DC output voltage, VDC, it is given by Vm by pi divided by 1 plus Rf by RL. So this is your average DC output voltage. I hope you are copying and noting down things. These are the derivations, which is very important and repeatedly asked. Okay. All right. We will stop at this stage and we'll continue our discussion in the further classes.
Ma'am,
Yes.
could you please show the equivalent circuit?
Equivalent circuit. Okay. Yeah. Yeah, Jason. You have any doubt there? You want to get it clarified?
No, ma'am.
Okay. Maybe what I'm guessing here is how did that RF come? Yeah. RF is nothing but the internal resistance of the diode. Assuming there is some internal resistance of the diode and replacing it with RF. RF is your internal resistance of the diode. So when diode is conducting there, replacing the diode with its internal resistance. So this will be your equivalent circuit when diode is conducting. Okay. So yes, we will go very slow here because these topics are very important and derivations are very important. I'll stop here so that you can go to your next class and we'll continue the discussion in the coming classes.
Ma'am, for a moment, can you scroll up once?